Yeah, let me start by the initial slide, which has the Universiteit Leiden, which is my home university, and the Cher Morlaix. I think that most people know the Universiteit Leiden, and I did notice that there were quite a few people that were not aware of the Cher Morlaix. But that is actually very interesting for you, since Cher Morlaix is 6 months, and it's twice Cher Morlaix holders every year, and you can apply for it. Already it's up now for 225 or 226, whatever. And I can really recommend it. If you ever become Cher Morlaix, you get a little fairy tale house in the woods here, so you're 10 minutes from the coast, and you're also 25 minutes by bus from downtown Marseille, which is the second city of France. So it's ideal. Of course, you need to take care of your things at home, that people can miss you, no small kids, no teaching, whatever. Take a sabbatical, and you're in... There's a sign by Samuele saying what?
You get a local host.
I mean, but you're not gonna get you. The minus is, of course, let me explain, Samuele was a little bit too quick. I was explaining what's going to happen. You become the Cher Morlaix, and to do that, you need a co-chair. And the co-chair actually is the really important person. That's why I'm pointing it out. And if you can get Samuele, that's ideal. Since it comes with lots of things, and yeah, there's 25 different sources of funding, of which 13 you have to take care of yourself. And they all come with different rules. So if you're without a co-chair locally in France, and typically the only rule I think you're not supposed to be French, which usually implies that you don't know how things work in France. So it's impossible without a co-chair. However, Samuele did it already. You'll need someone else, so look around, you're in Marseille, and well. Okay, so then you're Cher Morlaix, and you organize a couple of schools and workshops and conferences together with your co-chair, and you make a whole semester, 6 months, and there's supposed to be some outreach as well. And outreach is then supposedly for other people. Now again, I'm staring at you, and I see the same people I saw, say, last week in Leiden, where there was even an Escher talk. And that's also weird. How can there be 2 Escher talks by 2 different people having almost the same title? That's because the Escher talk has been around for almost 20 years. And it has been given, well, I would guess, between 200 and 300 times by a dozen of different people. It's been on 5 continents and at least 5 different languages. We have separate people, since the idea is that you always take the local language. You can have it for high school students or whatever you want. So don't use English, go for the local language. That's sort of a basic rule for Escher talks. So if it has to be Italian, you ask René Schoof, or yeah, depending where you want to go. And you may wonder, why am I talking English? I know that some people would have been happy if I had spoken French. I also know that some people would have been unhappy if I'd spoken French. And the only reason is that there's also someone in charge of the Cher Morlaix. And this lady is actually not here this week because she's celebrating her birthday back home in Germany. I'm talking about Caroline Pfaff. She's also great, but she does have opinions. And she felt that at a scientific institute, of course, the talk should be in English. So we're doing this for her. And I know she would be watching me on live stream, but she isn't. But still, I don't dare to switch. And also the slides are in English, so we have to stick to English. So maybe some other time. Too bad for that. It's also a change in France, since this talk, as I said, when I gave it the first time in France, I think that's at least 15 years ago, it was in Paris, Beaubourg, the Centre Pompidou. It was a day with la face cachée des mathématiques. And it was all French. Nobody asked whether it had to be in English or anything. In those days, we still were French in France. But just like we are English in Holland, you're now also English in France. Such is life. All right. So, too bad, it could have been a French talk, but you see the difference is actually pretty minimal. You can give it in any language, since the essential thing is the images that you're going to see. Since it's about Escher and Droste, and the name Escher you probably know, he's a sort of a well-known artist. Droste, you may have heard about it, but you need to be Dutch, I think, to really know. And I'm going to introduce these 2 main characters in this order. First Escher, then Droste, and then what the relation is. So Escher is just a reminder, since most people, you don't need to be a mathematician to know who Escher is. He's a graphic artist, born in 125 years ago, Dutch, and he died almost 50 years ago. And during his life, he produced many pictures, lithographs, woodcuts, and just to give you an impression of what they typically look like, they have a mathematical flavor, whatever that means. So here, when he came back to the Netherlands, he spent, as a young guy in the 30s of the previous century, he spent lots of time in Italy, Malta, So his landscapes tend to be sort of Mediterranean. We'll see the various houses. But then he came back to Holland, and Holland looks like this, very different. It's flat. And you see a few of the themes that you're going to encounter in much of the works of Escher. So the flatness of Holland is clear, and the long meandering rivers is also a Dutch characteristic. The towns are a bit small, a bit larger than on this picture, but still there's lots of meadows and cows that sort of make up the country. And the way Escher plays with this is that so you see all these squares, it's a very neatly arranged country, but then the birds in the sky, they actually form a tessellation of the plain. And that is something that Escher liked a lot. So in this case, they fly both ways. They fill up so with these animals, who actually fills the plain in a sort of a funny way. And also the meadows, the squares at the bottom, they gradually develop into the birds on top. These are the themes. He has many woodcuts that are called metamorphosis, or something like that, that actually transform things gradually into something else. So these characteristics we're going to see in the thing we're going to discuss in more detail. I'm going to give you a few more examples. There's also this tension between 2- and 3-dimensional. You see there's again the tessellation in the back. Yeah, you see the white and the black guys that sort of fill up the plane. They detach themselves and they go around whatever it is. And it's called encounter or something, ontmoeting, in front where they shake hands. Another one, you see the tessellation here is very clear. It's the standard hexagonal one at the bottom. You see the lizards, and what happens, the 2-dimensional plane, the lizards detach themselves and they go a circle and get back into the plane. This circular thing is also something that Escher particularly liked. Yeah, it sort of gives a closed feeling. The self-reference, also here the same theme again, the hands that detach themselves from the plane and they're actually drawing each other. So it feels a bit, this is not mathematical, but still it's a special kind. This is what he's really famous for, that is playing with perspective. If you look at the building, this is not at all a Dutch building. You can see where he spent a lot of time. It's vaguely Mediterranean, and it looks like at first quite a normal building. Typically there's always a guy in many of his pictures that sort of watch what he's doing, so this kind of person just looking, what am I seeing? And at first sight it may not be so clear what you're seeing. There is this building and these monks on the stairs, and do they go up or down? And if you keep staring for a while, it's not so clear. They go around, and in one direction they go up, and they also go down. And then you start really puzzling what's happening here. Something is wrong, but it's not immediately clear what is wrong and at which point in the picture it is wrong. And typically there is no point in the picture where it's wrong. In a similar way here, this is the Belvedere, the same kind of Escher-like building. And locally everything is fine, but globally there is a problem. If you want to point out what the front side of the building is, it depends. On top it seems to be where the lady stands, but then you go down and then the guy is watching in another direction. So somehow it doesn't fit. But you cannot immediately point out where the problem is. So this perspective playing is one of the favorite things that Escher likes. And he also gives a hint. Yeah, there's some kind of humor. Typically you see the guy with the cube here, and that cube holds the secret a little bit to what is happening. Yeah, you can sort of play with perspective just by getting a cube and make things cross the wrong way. If you do it on a more global scale, then it's not so clear what is happening, but you do realize immediately that there is a serious problem with the perspective in this picture. Again, here of the same nature, it looks like a pretty normal picture. Yeah, and again, there's the guy standing, watching the whole thing at the bottom this time. And in case you didn't realize what the problem was, you can even animate it, as people like to do it. And you see that the water, which is falling down and going up, it's not so clear what actually is happening here and how the whole thing fits together. That is what Escher is known for. In his later life, in the 50s, he encountered mathematicians. There was an exhibition at the Congress of Mathematics, the World Congress of Mathematics in the 50s in Amsterdam. And there was an exposition of Escher's work because it was so mathematical, whatever that meant. And then he actually talked to mathematicians, and mathematicians will say, oh, that's not a normal tiling, this is the hyperbolic plane. And indeed, the hyperbolic plane, if you know what it is, that's the way you can tile it. And in his case, of course, it's done with angels and devils. The final one before we start the actual topic of the talk, that is also to prepare you for what he likes doing, Yeah, there is a normal picture, there, yeah, sort of straight, normal perspective, and then as it seems in this picture, from the back, someone is actually pushing in a big sphere, and that, yeah, transforms everything in something funny. So the balcony is now standing out at a different size, and there's a gradual, yeah, deformation of the whole picture. And that is something we're also going to see in the picture that's the topic of the talk. That's a single picture that I will concentrate on for the rest of the talk. Is the print gallery from 1956. And that's a picture that looks like this. And again, you see that the world isn't exactly straight in this picture. So again, just like in the balcony that we just saw, he has been playing with things. There is a strange white hole in the middle that really is sort of strikes you immediately. Why is there a white hole in the middle? And the picture is also a little bit weird. There's again this self-referential aspect. If you enter this print gallery, so you go to the entrance, which is down there, and then the artist sort of leads you, your eye follows the print gallery, and you end up at this guy who's watching. Well, you don't exactly know what he's watching. Probably he's watching this picture. You might also be watching the lady, which is over there. We don't know, we are looking at his back. And that picture that he's watching, also, if you go around the white spot, you see that he's looking at some kind of harbor front, and the buildings expand to the right, and you discover that the utmost right building is in fact the print gallery itself. It houses on the ground floor the print gallery. So you see you're around, and apparently he is looking at something, at a building that he's standing in himself. And again, that looks a bit paradoxical. So the question is, what actually is happening here? And yeah, how did Escher create this? So first of all, it's a lithograph. So the original stone still exists somewhere up in an attic in the US, I think. And you see that a lithograph is from a stone. You see the picture, which is reverse, of course, because you have to print it. There is the obvious hole in the middle, the white spot. And the cross is because it has, can no longer be used to print more copies of the print gallery. Yeah, it's a finite print run, and what happens if you look at the picture, the hole, the white hole has been used for something, and if you zoom in, you see that it was created in May '56. There are his initials, that's part of the print, and this particular copy, of which you see a photo, in fact, that has a signature of Escher in the middle, MC Escher, and this is number 20 out of a print run of 47, and the 2 stands for the second print run out of 3, I think. So it's about 150 copies, and this is the copy having this unique number. All right, so the questions we're going to ask are, what is the structure of the picture, whatever that means, and also what the funny hole is supposed to mean. So here are the questions. And if you want, these are, of course, vague questions. They're not exactly mathematical at this point. You can just answer the first question by saying, well, that was a stroke of genius, and he just did it that way, and in one afternoon he had this fantastic lithograph. And why is there a hole in the middle? Well, he was an artist, and yeah, the universe of the artist, we don't know. It was what he saw, that it should be there. This is the only way it can be, because it's his view on whatever. This is the artistic answer, but we're going to answer the question in the line of someone else, the one that started the project, which is Hendrik Lenstra. And 20 years ago, roughly speaking, I think this is an Oberwolfach picture from 2005 or 6, I would guess. He asked these questions in the beginning of the century. This was the time when he was starting to move back from California, Berkeley, where he was working, back to Holland. And he did it sort of on a part-time, 6 months, a bit like the Cher Morlaix. You sort of have finite length things. And finally ended up in Holland, as things go. And during these long flights, Berkeley to Amsterdam is, San Francisco to Amsterdam is a long flight. He once had an airline magazine that showed this picture of the print gallery. And being Hendrik, and he didn't have much else to do, well, of course he did math most of the flight, but there was also time to think about Escher apparently. And he wondered, what is the structure of the picture? So what is happening here? And we'll try and answer that in his mathematical way. So first of all, how did Escher create that picture? And that is something you can discover by going for the sketches in the archives that still exist. So on the left you see it's ontwerptekening, that's a sketch for the design. This is transparent paper that you can use for the lithograph. And you see that this is essentially what the picture looks like. And the way he created it was using a grid. The word rooster, left lower corner, is Dutch for grid. That is what he used to actually create this funny rotating kind of picture. And you see the grid also has a hole in the middle. And if I say that he used it, if you put them together, they get a little bit smaller, you really discover, if you stare for a while at the two pictures, that there's many lines that you see. For instance, this line that you see here in the grid, it occurs, it's part of the window, it's exactly the same line. And the longer you look, you see that all the lines sort of are really used to fit the picture into the grid. So, mathematically speaking, the question is, what is the grid that you're using? Yeah, you like abstraction, you think, okay, the whole building scene doesn't interest me. What is the structure of the grid? If that's a meaningful question. And if you go to further sketches, you see that he actually did not immediately make a design of a curved world. He started out with a print gallery that was perfectly normal. And he used that to actually fit it into the grid. So that means that, you know it's going to expand from right to left. So if this is where you start, if you go all the way to the left, you need more detail for the window that you see here. So you need a different sketch that focuses on the window, and it really gets complicated if you look at the picture. So again, here, the picture needs more detail. Sorry, that was this one. And there you also see, if you can read the small print, that what you're looking at is actually a harbor front that is taken from Malta, where he spent some time. There's a ship, and you see in a normal way what all these buildings look like. If you move all the way to the right, then you will need more detail if you're going to expand it in the grid. So then you're ready for your next sketch, and you discover that the final building where you will need more details is here, and that's in fact the building that at the ground floor houses the print gallery. And if you want more detail for the print gallery, well, then what you need is the sketch from the beginning. So you see that after 4 steps, you're just back where you were. And what is happening here, you can read it in the book. The book is by Bruno Ernst. That's a good friend of Escher. The Magic Mirror of Escher is the title of the book. It was published a couple of years after Escher died. And he explained that the way Escher proceeded was really by taking all these various squares. There is a straight world, that's what you see on the right, that's here. And you really copy what's in the small squares from the real world into the expanding squares from the grid. So that's the way he did it. And this is a way to suggest this. Every time you have this sort of grid, and when you move sort of from right lower to left lower, you expand everything by a factor 4 if you look carefully at the grid. And if you do that 4 times, you get back to where you were. So that is something, a picture that apparently if you go around and you multiply by 4 times, you're back to where you were. And that is where the word Droste comes in. Since if you're Dutch, then you call this a Droste effect. And the scaling factor for Droste apparently is 4 times 4 times 4. That's probably 256. So the discovery, if you want, is that in real life, the picture that we're looking at must have been a Droste picture. So let me take some time to explain what a Droste picture is. First of all, if you don't know, you can just type Droste. And then you end up on a website. This is the modern website of the Droste factory in the Netherlands. And what they produce is chocolate. And it's in Dutch. They probably also have an English version. There's a little flag on the right upper corner, so you can have it in your own language. And everybody in Holland knows, if you read the Dutch, that this is our classical and delicious Droste cacao. And who hasn't grown up with that Dutch chocolate? Well, many of you may know, maybe didn't grow up with that kind of chocolate, but I certainly did. And the second sentence, it's still available in the original packing. So you can still get the famous Droste box, which has the nurse. The nurse has been updated a little bit, if you look at the right corner, with respect to the old box. But in principle, nothing has changed. And these chocolate makers, they actually do know that the Droste effect is something which is pretty famous, not only in Holland. So you see the website has the Droste effect, and there it explains that first of all it occurs in the dictionary, so it's a real expression that everybody should know in Holland if you claim that you should know Dutch. And what does it mean? Het Droste effect gebruiken, using the Droste effect, means literally that in your picture you reuse the same picture. And by that repetition you get an infinite picture, whatever that means. So that's what the Dutch says. That's very complicated. Of course, the rest of the Droste letters is what you get at Santa Claus in December. It's a seasonal thing. You learn lots about Holland. There is the rich history of the whole factory, all kinds of interesting things that I will skip now and focus on the Droste package. And you see the Droste package is indeed a package where the nurse holds a tray which has again a Droste package, which is the same picture repeated inside the picture. And that's the whole thing about the Droste effect. You just have a repeated picture. And there's a certain scaling factor. You see pretty rapidly the box on the tray, of course, also still has the nurse with a tray with a second box. And the number of boxes is actually infinite, but the number that you can physically see is very finite. And depth 2 in this case, the scaling factor I think is about 6.5. So 36 is quite a lot. And very soon you notice that your resolution is not sufficient to see the next box, or your eyesight may not be good enough to actually recover what should be there. However, there is a solution. And that solution is part of the Escher project, namely, you just zoom in to count the number of nurses that actually exist. And if you do that, like this, you can start counting. And indeed, the Droste website was right. The number of nurses that you see is really infinite. We're not going to see them all, so that would take an infinite amount of time. And you can also wonder why the movie that zooms in doesn't lose resolution in the end. And you can say, well, there must be a reason why. Of course, after all, it's a periodic video clip, so you needn't lose resolution, but how would you do this? And there is something, yeah, so you can, so we have this program to play with these things. You should also realize that to get one of these boxes to carry it, the number of nurses on the other side is also infinite. It's two-sided infinite. So counting nurses, whatever you do, is really going to take a lot of time. So that's the Droste effect, and we are proud of it in Holland. If you can be proud of your own nation, it's something that became part of the language. The Droste effect can occur anywhere. So this is a newspaper clipping, and if you try and read it, it happens to be in Dutch. Of course, the Droste effect being Dutch, we can just use it in a newspaper, and there's no relation with chocolate or anything or nurses. In this case, it's about the stock exchange, the Deutsche Börse, the German stock exchange, that actually has its own stock at the stock exchange. And it says it's like a dentist taking care of his own teeth. It's sort of a self-referring thing, and the Droste effect that's what it's actually supposed to mean. And Droste or Escher talks are given all over the world, as I said, and Hendrik was working in California in those days. So if you ask Americans of their favorite example of a Droste effect, you shouldn't call it Droste effect, but explain what you need, and then everybody has an example. And apparently the canonical example in the US is the Land O'Lakes, that's the butter. And this is actually a woman that has a name, she's called Mia. And Mia was invented, I think, by the Land O'Lakes, the dairy company in the 1920s. She got updated in the 1950s by a Native American artist that actually decorated her in the way his tribe used to decorate with all the beads. So don't ask me the details, he was proud of it. And that became the Land of Lakes lady that all Americans know. And you see that she's carrying the butter in her hands, and we know already what to do, namely, if you want to see how many butter there is, then you go and transform the whole thing into a movie. So the American Droste effect movie looks like this. And of course, it's all a matter of taste, whether you prefer the nurse in Holland or the Native American lady. Mia, or there may be other examples, but for many years we used this one. And I was very surprised when last year, when I was at Utah at PCMI, that Mia no longer existed. Since on the shelf there was Land O'Lakes, and rather than having this sort of nostalgic Minnesota, Land O'Lakes actually is Minnesota, that's where the company was. It looks a bit stern, and it's farmer owned, the land or the lakes or both, or the company, I don't know. And this Minnesota butter is now produced in California. And you do need to know apparently that it uses real California milk. Maybe there was something with fake Californian milk, I wasn't informed, but that's what you need to know. And the whole thing about rich and creamy is also disappearing now. It's really 100 calories per tablespoon. And you need to be American to know what that means. A tablespoon is an official unit in their system. Okay, and the last time I gave this talk, I think it was over a year ago in Italy. And there, of course, I still happily used the Land of Lakes and Mia. And in preparing this talk, I actually Googled a little bit what happened to Mia. And Mia ended up in US controversy, apparently. She was removed by Land of Lakes, and many people actually had opinions on this, and I will happily refrain from these opinions. It's probably an internal US thing. But I felt, given that the audience also include North Americans, that maybe I should not use Mia for this talk. So, yeah, and also given the fact that what Land of Lakes did, they put a white spot in the middle. And for our Escher talk, the aim is actually to get rid of the white spot. So this is actually going in the wrong direction from an Escher point of view. So maybe Mia from now on is out, and we need something else. And fortunately, I've given this talk more often for different audiences. And in Germany, in Erlangen, long ago, there was a lady that came to me and said, yeah, I know an example. Since when I was much smaller, we had this cheese, and the brand name was Roodkapje. You may recognize her, and they sold Camembert. And they had these bags, but also there are these cheese boxes, and you know what the Camembert cheese box is supposed to look like, right? It's a circular thing, and it's sort of this crispy stuff. It had to look like French Camembert. And she actually gave me one of these boxes. And that's what it looked like. And you see that Roodkapje, this is the light version, which only has 13% fat, but in principle it's Camembert, light Camembert. And it's actually quite a beautiful one. Maybe this is even better than the original Droste. Anyway, I was very happy with it. And I thought maybe that's a good one. But given what happened to Mia, of course you don't know what they will find out about Roodkapje. And if Roodkapje gets cancelled, we're in trouble again. So I did some homework yesterday and the day before yesterday, rather than going to all these great AGC square T talks. Hey, Samuel, I did it. I actually did a background check on Roodkapje. And so here is some essential information that you do need to know about Roodkapje to agree that we can actually use her for an Escher talk. As it happens, that I thought was funny, 1,000 years ago is the first time that Roodkapje, as she's called in Dutch, or le petit chaperon rouge, there's also a French version, and there must be an Italian one, Cappuccino Rosso, whatever. Cappuccetto Rosso, thank you, Mia. Okay, so rather than Mia, we have Cappuccetto Rosso. And she was born 1,000 years ago in the sense that she occurred in the works of Egbert van Luik. And I don't know whether we have Ronald van Luik, but this may be one of his early distant relatives. Egbert van Luik, and he has a Latin name, Egbertus Leodiensis. Luik you should recognize as the city in Belgium, which is called Liège, I think, in French, and also in English, and the Germans say Lüttich, and probably Italians have something different that I don't recognize. Mima can think about it while I continue with Chaperon Rouge. She occurs in this book that appeared 1,000 years ago, Fecunda Ratis. Ratis is a raft or a ship. Fecunda means it has a rich load, and the load consists of stories. It comes in two halves, the front and the back part, they're called. The front part is the secular classical stories, and the back part are the religious Christian stories. That's the balance you need to make in the 11th century. And one of the stories is about this girl, the Puella, that actually is sort of hijacked by a wolf in the forest and taken to the nest of the wolf. And because she has this chaperon rouge, this red hood, she is actually recognized as someone you shouldn't touch, and she's saved, and that's a great story. That's the beginning. For the French, it's a very French story, Charles Perrault. These are the, I think in English they're called Mother Goose Tales, maybe. 1697, that has a slightly different story. The grandmother actually gets into the story. It has an unhappy ending, but then there's Grimm, the brothers, a century later, the Kinder- und Hausmärchen, number 26, has the same story with a happy end. And we in Northern Europe like the happy end, so for us Grimm is the standard. And I think it's an established fairy tale character, and we can actually use or abuse her for this Escher talk. For those people who think this is too Eurocentric, I'd like to refer you to a scientific publication, 10 years old, using phylogenetic methods, if that's what it's called, That goes for the non-Eurocentric traces, and apparently it is not Chinese, but it might be that from the Middle East there is influence. But that would lead me too far afield, and we're happy to use Roodkapje, Little Red Riding Hood. So we now also have a movie, a clip, and as you see, it's a really beautiful one. This is the German Camembert, and I think that Caroline Pfaff, had she been here, she'd be happy that this German product is being advertised. However, there is again a slight problem. Namely, first of all, I tested it last night over dinner about German Camembert. And if you mention this to a French audience, German Camembert, they sort of stare at you. What do you mean, German Camembert? Do they have Camembert? Are they allowed to have Camembert? It cannot be good. And also, the way if you want to actually try it, you need to order it. And by now, it looks like this. This is the modern version. So it's without gen technology, whatever, and it's 55% fat, and it comes in 2 halves. It looks very un-French. And also the Droste effect is less visible here. It still says Roodkapje Camembert if you look at what she's holding, the basket. But it seems that my beautiful picture is a little bit old-fashioned, and also it's the wrong kind of Camembert. So the question is, what do we find in Marseille? Something local. And usually I give this talk and then I ask people, and then the next day I get emails from, yeah, we have this, we have that. But being in Marseille for so long, I already discovered it all by myself. Namely, I bought the beer at the casino, and the beer at the casino has this local brand, La Cagole de Marseille, and yeah, so you stare at this, La Bière du Cabanon, so you have your whatever, your log cabin looking out over the Calanque. And if you drink it really cold, c'est-à-dire glacé, you have a great beer. So, and as you see, it has an obvious Droste effect. So we're all set. However, being careful, I thought, let's do a check. So you look at the bottle, here's the back side of the bottle. And it's indeed local, so you can read the French. It has positive things over La Cagole. Yeah, it's not like the blonde fadasse, it has a brave character, so that looks pretty good. And, well, it's all very French. It's even the local French, right? There are words that are typically from the Marseille du Sud. And it's also the French sense of humor that really is visible from the bottle. But it only has positive things about La Cagole. And last month, Hendrik Lenser was here, and we walked around in the Vieux Port, and there they sell all these fridge magnets, and one of them had La Cagole. So we thought, we're probably safe, you can use this. Of course, as naive Dutch, but you don't even know what La Cagole means. So just a final check, a linguistic check. The first line is what you find if you, being French, in the old days you had Le Petit Robert on your shelf, and if there's a word you didn't know because it came all the way from Marseille, you pick the book and have a look. And then you get this line. So it's about women, and you may have noticed there was a woman indeed on the label. And there's a longer text that I also got from the internet. There's this word stereotype that makes it a little bit tricky, so you have to be careful. So it describes what a cagole is. So let's say a woman having certain properties that I don't need to go into in detail. Maybe the important thing nowadays is let's pas marcher sur les pieds. That's exactly a positive aspect that you should encourage, I think, in women. And the word in the old days used to be very negative, très péjoratif. And there are words that you're not supposed to pronounce in a sort of civilized talk for whatever audience. However, the word cagole a perdu, so it lost over time its insulting edge. So by now, I think the word cagole is okay. So given this background check, I thought, okay, let's do it and see what happens. So here is the corresponding, oops, okay, wrong button. And you see, you can do exactly the same thing. So the way this happens is that you get the fridge magnet and you make sure you ship it to Leiden, for instance, by going there yourself. There's still Willem-Jan Palenstein, who already 20 years ago was a student in Leiden. He finally came back. He's now working at the computer science department, and he engineered this beautiful video clip of La Cagole. So now we have sufficiently many examples of the Droste effect to go back to Escher. Namely, where is Droste in the Escher picture? Since from the actual picture it's not so clear, I convinced you that it came from a Droste picture, but it doesn't look very Droste-like at this point. So can we also find the Droste structure inside the true Escher picture? And in principle, what you can do, of course, you can undo what Escher did. So you take, as suggested in the book by Bruno Ernst, the grid, and you retransform the curved picture to the original world, and you discover the corresponding Droste picture. And if you do that, so then you use these, this is what you get. This has been done. Okay, yeah, that takes a little bit of actual work, of course. Also, it's not extremely beautiful. You notice that Escher was really doing this by hand, and things that were supposed to be straight are not exactly straight. Also, this hole in the middle, the white hole, now comes spiraling out, and you see that the text that was copy numbers such and such is now a spiral that comes out of the picture. And you see that what is lacking is, yeah, the content of the hole in the middle, but it does indeed look like an Escher picture, since if you zoom in, and after a while you end up with the original picture with the guy standing there. And once you have this picture, yeah, so this is again the first thing that I showed, it's relatively easy if you know sufficiently many local graphic artists to improve the picture a little bit, so to straighten it out. And what we did in those days was actually get pictures that were, yeah, straightened Escher pictures. And that is what the print gallery came to look like. Of course, you have to fill in the white part, so some additional pictures were added by these graphic artists, Escher pictures, maybe that were later. They had lots of fun doing this, as you can imagine. And the final touch is then the grayscales that were added, and you see that what you get is something that is transformable into a movie of the kind that we already know. So you see the real world Escher picture is indeed a Droste picture. And the only thing that we discovered already is that the scale factor, yeah, by which it repeats itself, is 256. So that means that if you stop it, and now there's a way to stop it that I may remember, maybe this, yes, then you see that the periodicity is not very visible, because if you look at the guy, the next guy is a factor 256 smaller, and there's no way to see this. So actually the movie only uncovers the infinite amount of spectators to this beautiful picture. All right, and in particular we haven't recovered the repetition that should occur in this Escher picture. Since it comes from a Droste picture, and even if you transform it in whatever way, the repetition should be there. So where's the repetition? So that's our next aim. And to discover the repetition in the picture, you compare the straight world from the sketches to the curved world that is created using the grid. And you see that if you take a square, like on the left, it gets transformed into something which is not exactly a square, but pretty close to it. It's just a little bit deformed. However, if you go for a bigger, say, rectangle here, you see that the image in the curved world is no longer a rectangle. It still has 4 right angles, but distances are not really preserved. It sort of looks a bit funny. And if you make it even bigger, and you go around this point, I should say, by pointing at this point where everything happens, then you discover that the rectangle in the real world becomes something which is no longer like a rectangle, topologically speaking. And that means that there's one point in the real world that occurs twice in the other picture. So this point here that you see there, is the same point as the point here. So that's what the repetition is. And of course the picture is a little bit irrelevant. You can just do it in the grid. If you look at Escher's grid and you walk around in 3 steps, left, 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 you're back. And in the same way, if you enlarge it a little bit, you get this. But if you take 10, it's different. And you replace 10 by 20, you get still the same 2 points that actually are going to be the same. So just by staring at the grid, you discover that there is a repetition. It's less visible. So the things that are, the stretch, the little thing that you see here in the middle, that points from the center to this point, corresponds, in the sense it's the same point as the long one that is designated by gamma. So this is 1 and this is gamma. And to phrase that slightly more mathematically, if you want, is that the print gallery itself is not an ordinary Droste picture. It is invariant not just under enlarging by a certain factor, you also have to rotate the thing. And if you look at the grid, you discover that the scaling factor, you see that if you compare the length. If this has length 1, that gamma is something like 18. And also, it's not quite the opposite direction. The angle is about 160 degrees, so a little bit less than 180. And this factor makes the copies disappear in the white hole. So the white hole, actually, it's a great artistic concept, but it just doesn't tell you what you want because it swallows all the information. However, there's again a solution that comes from France, and now we're on the safe side. This is French cheese, la vache qui rit. Everybody knows it. And la vache qui rit, this is not the most modern package, it still has the ham, but all the packages that you find in the shops have the property that there's a laughing cow. That shouldn't surprise you because la vache qui rit means the laughing cow. And the laughing cow typically has earrings, and these earrings are the packages that you're actually staring at. So there is a repetition, but there's also a problem. It's not the same picture. Yeah, the cheese, of course, is in a round box, as it should be. And the earring, which you see in perspective, is no longer a circle. It's an oval, right? It's an ellipse. But there's a solution to almost anything, since you just look at the box in perspective in the same way. So in this way, you have an elliptic vache qui rit box, and then you discover that what you do, if you zoom in while rotating, and that is what we're going to do now if we create the little movie, you see that zooming in and rotating at the same time does give you a video clip that repeats itself. So again, you can count the number of cows and enjoy the infinite aspect of this picture. So this is the Escherized version of the Droste effect, and it occurs in nature if you define nature as vache qui rit cheese. Okay, so what else do we still need to know? So now we understand what happens. So to fill in the hole in the middle, what you need to do is just enlarge, or in this case maybe make it smaller while rotating and fill it up. If you do that, this is what you get. And the scaling factor being 18 makes it still pretty complicated to see that the guy actually is in the middle. So let's go for the movie again and actually zoom in. And there you see that indeed you find the guy staring at the picture, and if you zoom in and in fact in the hole while enlarging, you do get a movie that repeats itself. So this is the hidden structure, if you want, of the print gallery, this Escher picture, and there is a sort of a completely obvious, if you want, at least your Hendrik, way to fill in the hole in the center. Okay, all very good. Escher is typically used as a kind of pep talk for young people, say, well, you need to know mathematics, otherwise you will never understand this. And where's the mathematics? And, well, given this audience, there's no live stream, so this is a pretty mathematical audience, and that's good, since now we get a few minutes of mathematics. Namely, what is happening here? The question is, mathematically speaking, what is the grid that Escher used? So here's the picture. Yeah, you want to go around and multiply every time by a factor 4. And how do you create such a network, such a grid, having that property? And that's a mathematical question, and Escher discovered, this is according to Bruno Ernst from the same book, The Magic Mirror, that he tried to do that using straight lines. And then he discovered that curved lines actually work better. Yeah, since if you look at the figure that we just looked at, you see that here you get angles that are no longer 90 degrees. So you lose the structure in a way. And what do you want? You want your small squares to remain square. And that should trigger a mathematical feeling. That's the property of what people call conformal maps. So what you want here is to construct a conformal map with this property. And so conformal map means that you start from a grid, you transform it in some continuous way in such a way that you keep the angles, so right angles remain right angles, but you can distort distances. That's conformal. And if you now go back to the mathematics of the Escher picture, you see that on the left you have the Droste picture, and you take the plane, and you remove the origin, that's 1 pixel, nobody will notice the difference, and you're left with a group, C star, and you want a picture that has the property that if you multiply by 256, you get the same picture. Which means that every pixel has the same color, if you want, as 256 times the picture. So the left is the code, the mathematical code for a Droste picture. And what we discovered is that the Escher version on the right, that is the same structure, only the multiplication is now by a complex number rather than by a real number. So there is some gamma, the thing of absolute value around 18 and whatever, it has an argument. And these structures are actually well known, say in AG C² T, as elliptic curves. If you mod out C star by a cyclic subgroup of infinite order then you get an elliptic curve. So you can forget about all the pictures and consult your local expert on elliptic curves. And what do? These people tell you, well, these are Riemann surfaces that are going to be isomorphic. In this map that we're trying to figure out what it is, the thing we need, that is something that you can lift to the covering space, universal covering space, which is just C itself, and the covering is via the exponential map. And then the question is, what does the map look like on that level? So the map alpha is the thing that we want to have. This should be a complex analytic map that makes the whole thing commute. And that isomorphism is in fact very rigid. Since you discover, if you want to do that, that the thing that you have on top, the exponential map is periodic. So that means that to push a picture down, you have to have something on top which has a period 2 pi I, being the complex period of the exponential function. And also because it is an Escher picture or a Droste picture, there is a second period. In the first case, it's the log of 256. Since you have to map to C star modulo, the exponential of the log of 256, which is 256. In the same, we have the log of gamma, which is maybe not exactly unique because it's up to 2 pi I, but the lattice at least is good. And you see that apparently you have two elliptic curves, and some people recognize C modulo lattice as an elliptic curve, and otherwise you just take it as a nice picture. And the rigidity of the situation is that the only thing you can do this is actually multiplying by a complex number. These are the only isomorphisms that exist between these complex analytic structures, these elliptic curves. And that means that the two lattices that you're staring at, they have to be, homothetic is the word. You just get one by multiplying it by a factor from the other. So if you stare at this picture, you see that alpha is just multiplication by some complex number, and the equations are staring you in the face. Namely, alpha is the element, if you multiply log 256, which is the thing here, by alpha, you get log gamma. So alpha is in fact log gamma over log 256. But it's also, for exactly the same reason, it's 2 pi I over log 256 plus 2 pi I. And if you take that together, you've proved a theorem in mathematics. And that theorem says that, this is two ways to write alpha essentially, you can just compute gamma. So Escher got pretty close. It should have been something of absolute value 22.58. And the argument, now in radians, since we're doing mathematics, is almost correct. And just by fiddling around, Escher could almost do it perfectly. Not quite, so here's what is happening. There is the normal grid at the bottom. Here is the logarithmic plane. What you do is just multiply on the top level by a constant. That's a rotation and an enlargement, and then you take the exponential map. That's what's happening. It also means that the grid that Escher constructed just by hard work, you can computer generate it. Have formulas. So these smart guys in Leiden that were good with computers could actually find the grid as it should have been to make it completely conformal. And if you compare what they created with the original Escher thing, you see that actually it's quite good. There are certain things that are not exactly as they should be. Here things are curving the wrong way in a sense, but overall, Escher really got close, and that's also visible if you compare the conformal Droste picture with what Escher created, and you go back and forth, this and that. You see that's really very close. So the mathematical structure has now been sort of understood, and that means you can use the math to actually create these nice movies that we made. And how does that work? Well, so here you see, this is the thing where you can actually, so these are the movies that you want to make. You zoom in and you rotate and you don't lose resolution. That is the aim of the whole thing. And same thing here. And you can also, what Escher did, you take a true Droste picture and you transform it to get something else. That's a lot of work. But in my case, I just hit a button and I can Escherize whatever I want. In the same way, yeah, maybe the nurse, so here's Roodkapje again, Roodkapje I should say, whatever you want to call her. She also comes with variants, yeah, like this one. That's an Escherized version of the German camembert. And you can actually do it in two ways. This one is also really nice. So in real life, you can create your own Escher artworks if you want, but of course you need to understand how this should be done. So also La Cagole, she has an Escherized version. Yeah, this one, or maybe that one. There's various ways to create pictures that are, yeah, of Escher nature. And how do you do it in practice? So this is the mathematics behind the video clips. This is a boring picture. It shows what a typical computer screen looks like. You just have pixels, and what you can do with these pixels, not much. There are easy things that are easy in the sense that, well, this is too slow, I think, for my old computer. You can translate, but if you have, or a computer you have to translate all these dots, it's really slow. And you can do it in two directions, the X and the Y direction, and it's very similar. And what you need is something different. Namely, you want to do two things. You want to zoom in, and zooming in is what I'm doing now. And you see that your pixels, you need higher resolution in the middle. Yeah, that's where the sort of the pixels should be dense to have all the information. And you also want to be able to actually rotate the whole thing while zooming in and out. So the movies that I've been showing are on a pixel level. This is what is happening. Yeah, you have a zoom in and out, and you have a rotation. This is what you need, and what you have on your screen is what I just showed. And what you need is, in fact, the exponential map. That is what the proof actually showed. Namely, the exponential map transforms these rectangles into, yeah, the shapes on the right. And that means that if you give them information, so you fill in the pixels in whatever way you want, you get exactly, here it becomes completely periodic, and you're dealing with translations, and here you actually have multiplications, and the nurse on the outside, yeah, so this nurse is much bigger, so here you need higher resolution. But on that tile, nobody cares. This nurse is identical to that one. So you see if you can use the exponential map from the left to the right, or conversely the logarithm to go back, as soon as you can compute logarithms, you can create these little movies. So what you need is a logarithmic plane that is tiled with your, in this case, Droste nurse, and you use that to create these pictures. And to create the thing on the right, there's two things you can do. You can zoom in, and zooming in on the logarithmic plane just is a horizontal translation. And you see that you can just look at the plane, and you only need one tile essentially, because it's completely periodic. And in the same way, there's another thing you can do. If you move in the vertical direction in that plane, what happens is that you rotate. And clearly that's also periodic, period being 2 pi, just what we discovered. That's what you want to do. And what is happening for La Vache-Curie, that is a Escher style Droste picture. And you see that what you do there is moving in the same way through the logarithmic plane, and there is a difference now between the logarithmic plane, since the periods, there is always the vertical one, yeah, there's the heads of the cow are always above each other, so the 2 pi I is just between the two noses of the cows, but the ham doesn't have a horizontal translation, you also need a rotation, so that means that there is a direction which is not perpendicular. So that's what it means mathematically on this logarithmic plane. You have a double periodic picture that you use to create what you need. And what I'm doing here is, if you have the picture like this, you define the distance between the two noses of the cows, yeah, the one here and the one here, as 2 pi I. This is the 2 pi direction. But you may as well tilt your logarithmic plane a little bit and say, well, maybe after all, I want these two noses to be distance 2 pi. And then you get a different picture. So this is the Escherized version, if you want, of La Vache-Curie. You can play around with these things, and you see that the cow, yeah, it gets a very large ear. It's more like an elephant, but the structure is actually the same. Namely, you get a different Vache-Curie thing. The symmetry is now, again, rotating while enlarging, and it's periodic, but of a different nature than the original one. And in that way, you can create many things. So Lacagol, if she is being transformed, this is the logarithm of Lacagol. And that's double periodic, as you see. So if you look at the beer, you see that this is the 2 pi I. Here's beer and there's beer. And this is the factor that gives you the enlargement. And that shouldn't be too big if you want to have a nice Escher picture. So we can do it in exactly the same way. So what I was just showing you, yeah, just a plane enlargement is what you get if you move through the logarithmic Gagol plane in a horizontal way. But you can also do it in this Escherized version. It just means that you tilt your logarithmic plane a little bit, and then the 2 pi is not in the same way, it's just tilt a little bit. You can also tilt in the other direction, and that's the other picture that I showed. So that's what's happening here. You have a logarithmic double periodic thing. You choose a 2 pi I, and that gives you all kinds of weird pictures. And you can use it, if you have your favorite picture, to create your own Escher thing. This is a leftover from the Italian version that I forgot to adapt, so my apologies for having the wrong language here, but there's also English. So, as I said, you can do it with the original. This is the print gallery, the logarithmic plane. You can tilt it, and you get exactly what Escher did, the Escher picture. But you can also tilt it the other way, and then you get a different picture. And if you want to see what it is like as a movie, you see this is also Escher, but now it's turning the other way. Of course, it's a matter of taste, whether Escher got the right one, or whether this is a better one or worse. And that's all up for your personal opinion, if you want. And actually, there's an infinite number of Escher pictures. As I said, you can pick your 2 pi in your own favorite way. So, the standard logarithmic plane for the Droste straight version of the Escher picture, that's here. But if you pick something else, this one for instance, then you get the Escher picture. But there's a whole plane full of things. So for instance, here's the straight world. Here you find it's square, it's cube. That really looks funny. It's inverse. All the straight lines become circles. And you may want to discover these. And to do that, you just feed it to the program. And you see that there's various Escher-like movies. Here is one example. Let me just, in view of time, I think I should almost stop. Show you a few of the examples. So this is the more classical one. This is turning the other direction, which is quite okay. Here's the square. It no longer rotates, and you get the guy twice. It has a symmetry. You can sort of go in between. This is already getting pretty wild if you move away from the origin. And the further you go away, the wilder it gets. I mean, this is another one in another direction, and if you really go far away, you get pictures that are really, well, you can spend a lot of time on this. I won't do it, but it's lots of fun. And this is only one picture. This is the inverse. That's also very funny. This is non-rotating, inside out. I mean, there's all kinds of Escher pictures. This may be the most beautiful one. Escher was an artist, right? But still, and if you don't like Escher, well, you go for whatever. Here's various versions of the Camembert, the German Camembert, but still, it rotates in funny ways. And you see, this is the square again, or a little bit further. And again, far from the origin. Oh, this is another one. And you see it gets really wild. And you can imagine what happens to La Cagole. If you don't like this offensive picture, you just transform in such a way that nobody actually recognizes. In the beginning, you still see her, but then if she gets squared or, it really gets very funny. All right, final thing, all in the beginning, 20 years ago. What can you do yourself? You create your own easy Droste picture. You just pose and you put a blank thing in the middle. So this is Hendrik's Berkeley apartment. And it doesn't take a lot of photoshopping. Maybe he did it himself, unlikely, but then one of his students could easily do it. You just put it over and over in again. And you say, well, can I have an Escherized version? And you click a button, and there you have it. This is something anybody could do. And you find them also on the web now. It's something which is not extremely complicated. All right, thank you very much.
Okay, so thank you very much. So are there any questions or comments or I don't know, so
Yeah.
The software where you can introduce these features, you said that this would be available online, or?
No, the software is probably latent property. Also, it has evaluated, so it has been evolving over 20 years. So it's not so as portable as it should be. This is the latest edition that now runs on my laptop by Willem-Jan Palenstein. Since after a couple of years, you get newer Macs and it no longer works. It uses all kinds of crappy old programs. And it's being updated at times. For instance, when you have to give an Escher talk again, you sort of, hey guys, I need it. And then it no longer works on your current computer, typically. And they help you, and then in the end, it does work. So, yeah, this is not something that is freely available at this point. But it may be because of our lack of enthusiasm to do so at this point. Yeah?
Thanks. Just a curiosity, you said that every time you give the talk, then there's always someone writing you an email, providing you with new examples.
Exactly.
So I was wondering, of the ones that we saw, I mean, how many more did you collect over time?
Oh, yeah, of course I'm not flexible because you write sort of a script for your talk. So I cannot show you the Colombian one, which is also really funny. That's the baking powder. I still need a good Italian one, by the way. So before my next Italian talk, if you can produce one, would be great.
no more questions? Okay, so thank you very much for this very nice talk and very interesting artistic talk. So thank you.
Thank you.